Okay, a couple things about basic wave characteristics, okay? In your math class, you might have studied what are called sine waves, okay, which just looks like a squiggly line going up and down like an ocean wave. We call the high point of a wave the crest of a wave, okay? If you're into surfing, you know you want to catch the crest of a wave, right? So you get the max amount of energy there. The low point of a wave is called the trough, okay? If the wave is perfectly at rest, we call that the equilibrium line. In a second, when we go out into the hallway, we're going to use the tiles in the hallway to line up our slinky, our big metal slinky, 25-foot slinky. And when you line it up with that line on the tile, that's going to be our equilibrium line. It's where the wave is at rest. Okay? And then once you disturb it by giving it a sharp snap with your wrist or stretching it to the side, you get a crest, and then as it snaps back, you'll get a trough, and then it travels on and on. Okay? The amplitude is the size of the disturbance from the equilibrium point. It's the size of the wave. So for example, let's say this is a 3-foot crest. So then that would be the amplitude, right? Or if you have a negative 3-foot trough, your amplitude would then be negative 3. Finally, we define what's called the wavelength, okay? And the secret shortcut symbol for the wavelength is not the letter W. That would make sense, but W is actually used for something else. So we have to actually go to the Greek alphabet. Okay? And a lot of times in science you'll see that since we have more than 26 ideas that we're trying to represent than 26 English letters, we go to the Greek alphabet. And the Greek letter that we use to represent wavelength is the Greek letter lambda. Okay? Which is, it looks like an upside down Y right here. Okay? And that represents wavelength. So one way you can measure wavelength is from crest to crest. Notice if I start here, pretend it's a roller coaster, I'm first going to go what? Downhill, right? And then I go back to the top, and then I'm going to go downhill again. So that's one wavelength. Somebody tell me what's another way to measure wavelength besides crest to crest. You can also measure from where? Yeah, trough to trough. Because notice now I'm going uphill, okay, and then I go back down, and now I'm going to go up again. So this is another wavelength, trough to trough. Okay, in fact, you can pick any 2 points, and as long as you start to repeat yourself, that's a wavelength. So I could pick this equilibrium point here, this 0 point, and as I trace this around, looks like this is another wavelength right here, because I'm repeating myself, and so on and so forth. Okay? Okay, finally, we can now define 4 terms, okay? Wavelength, represented by the Greek letter lambda, is the distance it takes for a wave to repeat itself. The metric units for length should be in what? Feet? Or in what? In meters. That's correct. Okay? And one interesting application of wavelength is looking at building antennas as well as satellite dishes. Okay? If you ever noticed, for satellites, okay, if you have satellite like dish TV, anyone have that? Like satellite TV? Okay? You got a little receiver on your roof. How does the satellite compare for digital TV signals compared to like a normal TV antenna? You ever notice? Which one's bigger? Your normal TV antennas are big, right? Okay, they're on top of your roof. They're kind of ugly, so some people hide them inside their attic there, right? And that's because the wavelength of normal TV stations, analog TV stations, is a lot longer, so you need a longer antenna to capture those waves. Whereas for dish TV, satellite TV, the wavelength's smaller. Okay, so it tends to be a smaller dish there. Next, we define period. The symbol we use for period is a capital letter T because a period is a time for one complete cycle. Units is in seconds. Okay, so period just means how long does it take for something to repeat itself. So for example, what is the period of the Earth's rotation? The Earth rotates once every what? 24 hours. Okay, the period of the Earth's revolution, or actually, is it revolution? Yeah, revolution around the sun. Okay, we go around the sun is once every what? 365 and a quarter days, if you want to be technical there, right? So on and so forth. Frequency. The frequency is the inverse of the period, okay? It's the number of complete cycles you have per unit time. Frequency, F, is equal to 1 over the period. It's the inverse. The units should be 1 over seconds, but that's kind of awkward, so we abbreviate that Hertz, HZ, okay, in honor of this car company. No, just kidding, okay? It's in honor of this great German scientist, okay, named Hertz, who did a lot of study about radio waves and frequency and all that. And in fact, you already know what Hertz is, yeah? Every time you turn on your radio in the car, how do you know which station you're tuning into? Okay, yeah, you look at the what? The frequency band, exactly. And it's in FM, it's megahertz, right? Ashley, what do you like to listen to? You like, which one? The Mix FM, which is which? Oh, Kiss FM. I'm sorry. Which station? 103.5. Okay. When you tune in your radio to Kiss FM 103.5, you know what you're doing? You're telling your radio receiver that I want to pick up radio waves that are shaking back and forth. How many times a second? 103.5. And then what's mega stand for? You guys remember? Mega stands for million. Exactly. So what happens is Kiss FM. I think they broadcast from the city, right? Okay. There's a radio station downtown that has an antenna that jiggles the electrons 103.5 million times a second to send that signal out into the Chicagoland area. And then when you tune in your dial, you're telling your radio receiver to pick up electrons shaking 103.5 times a second. Okay? Contrast that to AM stations. Anybody ever notice on the AM dial what you're getting? Anyone listen to any AM stations? Like sports or news or whatever? Okay. Radio Disney, there you go. Okay, or talk radio, sure. And what do you notice? What's the band? It's not megahertz for AM, it's kilohertz, exactly. Okay? So when you tune into, Christine, what do you like to listen to on the AM band? 890. Okay, when you tune into 890, is that talk? Okay. Kilohertz on the AM station, it's 780,000 times a second. Or Ellen, if you do the Radio Disney thing, what's that one? Is that like AM 1300, exactly. Okay, it's 1,300 times 1,300. Actually, AM 1300. You have to add on 3 zeros. So let's see, 1300. It'd be 130,000 times a second, and so on and so forth. Okay. Finally, we can come up with our second equation for this unit: wave velocity v. Okay, we've studied velocity. It's just a fancy word for speed. The speed which a wave travels at is simply equal to its wavelength times frequency. If you know how far a wave will cover, okay, as it repeats itself, and the number of times it repeats itself every second, if you multiply the two, you get meters. Frequency is 1 over seconds. That gives you meters per second. Okay? So why is this useful in real life? Well, when you're designing a radio station and you have a certain size tower, you know the speed of light, which is how fast radio waves travel, 3 times 10 to the 8th meters per second. If you know the frequency that you're licensed to broadcast at, you can pick the right length antenna to optimize your broadcast set, and so on and so forth. Okay? So today we got a lot of definitions. Okay? The best way to learn is actually by doing. So in a second, we're going to head out in the hallway with these giant 25-foot slinkies. So I'm going to give you a couple tips. And you're going to try generating waves of different lengths, periods, and frequencies to get a feel for how basic wave properties work there. And there we have it.